Welcome to The Explainer. Today, we're doing something a little different. We are completely flipping our perspective on the periodic table of elements. Let's stop looking at it as just a chart on a chemistry classroom wall and start exploring it for what it truly is, the ultimate interactive map of the universe's building blocks. And when I say building blocks, I mean literally everything. 118. That is the sheer scale of our map today. There are exactly 118 known elements that make up absolutely everything around us. I'm talking the oxygen you're breathing right now, the silicon inside the device you're using, the whole shebang. And what's absolutely amazing is that they aren't just thrown together randomly, They are arranged perfectly by their atomic numbers.
So, to navigate this, here are the 4 key landmarks we're going to visit today. 1. The ultimate chemistry map. 2. Periods and groups explained. 3. Metals, nonmetals, and metalloids. And 4. Tracking periodic trends.
All right, let's jump right into our first landmark, the ultimate chemistry map, arranging the building blocks. So, the golden rule of this map is that elements are arranged in ascending order of their atomic numbers. Now, interestingly, this wasn't always the case. Early chemists like Dmitry Mendeleev actually tried arranging elements by their atomic mass. It was a good try, but it definitely had some holes. But then, in 1913, a scientist named Henry Moseley discovered that using the exact atomic number, which is just the number of protons in an atom's nucleus, completely resolved all the flaws in those older tables. It was a real game changer. So, as we read our modern map moving from left to right, the sequence of all 118 elements is strictly driven by an increasing atomic number. 1, 2, 3, and so on.
Moving on to Section 2, Periods and Groups Explained, or what I like to call the latitudes and longitudes.
Just like a map of the Earth, our table has its own grid of horizontal and vertical lines. First, we've got the 7 periods. These are the horizontal rows. As you travel left to right across a period, you'll see the physical and chemical properties of the elements gradually change. Then, cutting right across those, we have the 18 groups, the vertical columns. Now, this is absolutely crucial. Elements living in the same vertical column share very similar chemical properties. They act a lot like a tight-knit family. But why is that?
Why do elements in the same vertical group act so similarly? Well, it all comes down to valence electrons. Basically, these are the electrons hanging out in the outermost shell of an atom, and they completely dictate its chemical destiny and reactivity. If elements are placed in the same vertical group, it's precisely because they have the exact same number of these outer valence electrons. So it is literally like a family sharing DNA. For example, take group 1. All the elements there have just one valence electron, which makes them all behave in highly reactive and frankly sometimes explosive ways.
Next up, Section 3. Metals, nonmetals, and metalloids, the elemental continents.
You can think of the map as being divided into 3 main continents. First, we have the metals. They live over on the left side of the map, and they naturally tend to lose their electrons, which forms positive ions. Then, on the completely opposite side, the far right, we have the nonmetals. Their behavior is the exact reverse. They absolutely love to gain electrons to form negative ions. And sandwiched right between them, acting as a sort of border, are the metalloids. Found along a stair-step boundary, these guys exhibit a really fascinating mix of properties from both the metals and the nonmetals.
To give you a vivid picture, think about magnesium powder burning. It reacts extremely rapidly with this intense, blinding white flame. Magnesium is a classic, proud resident of the metals continent. Specifically, it's an alkaline earth metal found in group 2. Because it's a metal, it reacts vigorously by losing its electrons to form positive ions. That reaction creates magnesium oxide in a brilliant display of light that is actually used in things like fireworks and emergency SOS flares.
Now, to clearly separate those fiery metals like magnesium from the nonmetals, our map has a very specific geographical boundary. We call it the stair-step line. It starts up top at boron and literally steps down all the way to polonium. The elements sitting directly on this line, think silicon or germanium, are metalloids or semimetals. They are nature's perfect middle ground, blending the traits of the 2 extremes.
All right, let's head into our final section. Section 4, Tracking Periodic Trends, Shifting Tides Across the Map. So, you might be wondering, how big is an atom anyway? And does its size change depending on where you travel on our map? Let's look at the push and pull of the atomic radius. Interestingly, as you navigate left to right across a period, the atomic radius actually shrinks, it decreases. Why? Well, because an increasing nuclear charge, meaning more protons, pulls the electron cloud tighter and closer to the center.
But if you travel top to bottom down a group, the radius increases, and that's because you are physically adding entirely new electron shells, which expands the atom's overall size, even with that heavier nucleus pulling inward.
Let's map out another shifting tide here, electronegativity. You can think of this as the power of an atom to aggressively attract shared electrons toward itself. This power actually increases from left to right across a period. Those smaller atoms over on the right side have a much stronger grip on electrons. Conversely, electronegativity decreases from top to bottom down a group. Because of this, the halogens, which are situated on the far right just before the noble gases, possess the absolute highest electronegativity values on the entire table. Fluorine, for instance, is the reigning champion when it comes to attracting electrons.
Now let's contrast the directions of metallic character. Moving left to right, metallic character decreases. We just learned that atoms hold tighter to their electrons on the right side, so it makes total sense that it's harder for them to act like electron-losing metals. But moving top to bottom, metallic character increases, because larger atomic size makes losing those faraway outer electrons so much easier. This proves that traveling down the map creates far more reactive metals. For instance, cesium, which is way down at the bottom left, is incredibly reactive compared to lithium right up at the top.
All of this brings us to a beautiful, overarching summary of everything we've explored today. The physical and chemical properties of elements are periodic functions of their atomic numbers. This is known as the modern periodic law. It perfectly captures how this brilliant design elegantly maps out all physical and chemical behavior simply by following the atomic number. It's truly a masterclass in natural organization.
So, we know the layout of the periodic table accurately predicts elemental properties for all 118 known elements. But science, as we know, never stops. So what happens when element 119 is finally discovered? Where exactly will it live on this map? And what incredible, totally undiscovered properties might it possess? The map isn't finished, folks. It is just waiting to be expanded. Thank you so much for diving into this explainer with me, and definitely keep questioning the building blocks around you.